Hi, welcome back. Today we will be discussing the really basic introductory concepts behind matter, atoms, elements, compounds, and the way elements bond together to form those compounds. So let's begin. Matter. Well, what is it? Well, matter is anything that takes up space and has mass. So matter is made of atoms. Now, there are things we interact with all the time that are not made of matter or don't count as matter. Energy in general fits into that. The sound that you hear is not matter. We can measure it, we interact with it. Sound can actually even make things move around because it is the motion of molecules. But sound itself is really just energy. Light is also a kind of energy, heat. Those things are not matter. Although in the case of light, it is made of particles, but those particles have no mass. I know. Then of course there's dark matter and dark energy, which we will not be talking about because it doesn't really have anything to do with biology, and I'm definitely not an expert. But we do have to talk about these other things because the study of life, the study of biology, begins with chemistry. Everything that you do, everything that living things do, is a chemical reaction, or the reason we can do those things is because of chemistry and chemical reactions. And the study of chemistry begins with the atom. So if you go way back, the concept of the atom is a very old idea. It goes back several thousand years to ancient Greece. The word atomos means uncuttable. So if you take anatomy class, anatomy is the cutting of the body, same root word. So the idea is if you take a material, any kind of material, and you break it in half, well, I still have two halves of the same thing. If I take that other half and I break it, still two halves of the same thing. Is there a point where if I take a material and I break it in half, the two halves are no longer the same thing? Yes. Now, that can be the case for more than one reason. For elements, it's the individual atom. So if you split the atom, well, that will turn into two completely different things. But also, the same is true for compounds. We'll wait a little bit before we get to that. So atoms are small and indivisible. By indivisible, we mean once you break the atom, it turns into something else completely. So that's what indivisible means. But atoms themselves are made of particles. The atom has all of the characteristics of whatever the element is. So again, if you break that atom in half, you no longer have two of the same substance. And atoms are made of these three things: the protons, neutrons, which are found in the nucleus, and electrons. The proton and the neutron have approximately the same mass. Indeed, virtually 100% of all of the mass of an object, no matter what it is, comes from the protons and neutrons. If I took all of the electrons away from a material, the material's mass would be more than 99.9% the same. So, we really only are concerned with protons and neutrons when it comes to the mass of an object, and we refer to this as its atomic mass. So that's the total number of particles that are found in the nucleus. But atomic number is special. This is just the number of protons that an element, or an atom or element's nucleus contains. And this is important because an element is actually defined by its atomic number. The periodic table goes 1 through 118. There are only 92 naturally occurring elements. But if we take copper, looking at my periodic table over here, copper has an atomic number of 29. That means that the copper atom has 29 protons. All copper atoms on this planet, on any other planet, anywhere in the universe, have 29 protons in them. If you somehow removed a proton, then it would become the element nickel, which has an atomic number of 28. for the individual atom, it would become a nickel atom. If you had a big block of copper and somehow from every single copper atom you took away a proton, not really possible. But if you did, the entire thing would just transform into nickel, which would be a pretty amazing feat. If you added a proton, then you would have the element zinc instead. So all elements, the only difference between any of them is, the only true difference is sort of how many protons they have, but then also they have different numbers of neutrons and electrons as well. And generally, for any atom, under normal circumstances, all atoms have the same number of electrons as protons, which makes them electrochemically neutral. The positive and negatives cancel each other out. The neutrons, those can vary. Now, in a living thing, what elements are you made mostly of? Well, you are mostly oxygen, but not oxygen gas or anything like that. Not oxygen all by itself. That oxygen combines with other elements to form compounds that make up your body. And those compounds include, as we can see on here, water, proteins, carbohydrates, fats, and then some minerals as well. You are mostly oxygen, and then carbon, hydrogen, nitrogen. Those four basic elements make up 96-ish% of you or of any other living thing. And then as far as compounds go, we can see those on here as well. Now, you're not really made of water. You contain water inside of you. You are made out of proteins, fats, carbohydrates, and then nucleic acids. That's what you're literally made out of. And same story with minerals. You're not, well, your skeleton has many minerals within it, but a lot of minerals in our bodies, we're not made of them. We use them for chemical reactions and other things. So again, an element is a substance that cannot be broken down into simpler substances. An element is made of one specific type of atom. The gold atom, the copper atom, the carbon atom, so on and so on. Now, this word substance is actually like a technical term. A substance is a rigidly defined material that only comes in one variety. So water is a substance. It's H2O. That is the definition of water. That is not the definition of anything else. Sugar's a bad example. There are many types of sugar. We could say maltose, for example. It has a very specific chemical formula and a very specific shape, and that alone is what maltose is. Hydrogen and gold are elements, H and Au on the periodic table. Sulfuric acid, which I think is HSO4. I may be wrong about that. But these are substances because they're defined by their chemical formula, or the fact that they are an element. But other materials, like the air in this room, air is composed of substances, oxygen, nitrogen, carbon dioxide, methane, but air is a mixture of those things, and there's no definition for what air has to be like. The air in this room is a different composition than the air outside, almost certainly. So it's not uniform. Soda, there are many different types of soda that you can buy, and they're all different. Some alloys, brass, steel, and bronze, those can come in a wide variety of forms. The gasoline you buy at the pump, well, it comes in 3 different octane ratings. It's got different formulas. They add materials to it. So these are not substances. And in nature, we virtually do not run into any pure elements or pure substances of any kind. Really, the only pure elements that we interact with is the oxygen in the air that we breathe. That's molecular oxygen, O2, and there's nitrogen in the atmosphere. We can't personally use it. We breathe it in, but it just comes right back out. And then substances as well. So water that you drink is never just pure water. There are always other materials mixed in with it. So because we virtually never find any pure elements, we have to talk about compounds. So a compound is a substance formed by the chemical combination of 2 or more elements. Now, notice I said substance. compounds are also rigidly defined. And I already sort of alluded to this in the previous slide. For example, H2O is water and only water. H2O2, it's made of the same elements, hydrogen and oxygen, but we changed the formula. That's not water. That is hydrogen peroxide. Do not drink hydrogen peroxide. Another key thing with compounds is compounds always, invariably, have very different properties than the elements that they are made of. So for example, let's look at what we have here. The substance, the material on the left, well, you can't actually see it because it's on fire, but it is sodium metal. So when you place sodium in water, it becomes molten and it can catch fire and explode, potentially. The other substance is chlorine gas. Chlorine gas is extremely poisonous, extremely deadly. I didn't say it, but you can assume by the picture that sodium is also really bad news. You would not at all want to put either of these substances in their pure form into your body. However, at least not in large quantities. However, when they combine together, well, sodium chloride is just salt. Not only is salt not harmful to you, it's actually necessary for life. You can't live without it. So two ingredients, which by themselves are lethal to life, combine together to form a necessary compound of life. But that's the nature of chemistry and compounds. When describing chemical compounds, we do this in different ways, and we will be describing all kinds of different compounds in this class throughout the year. So we can use their common name, their chemical name, or their chemical formula. So water, you will never hear me call water dihydrogen monoxide ever again, but technically that is its chemical name, or we use its formula, H2O. Sugar, there are many kinds of sugar. Glucose is one of them, and its formula is C6H12O6. Rust, not really a compound associated with life, but rust is iron oxide, is its chemical name. Its chemical formula is FeO2. Now, if we go backwards here, how does hydrogen and oxygen, how do they combine together? Well, atoms, the only way for atoms to bond is through interactions between their electrons. The nuclei of the atoms never get close to each other. On the atomic scale, the gap between where the nucleus is and where the electrons are, the electron cloud will be, is vast. It's extremely vast. So we'll talk about two very basic kinds of bond. Well, we'll talk about the basics of two types of bonds. So an ionic bond occurs when one atom steals one or two electrons from another atom. Now, because electrons are lost or gained, that means that now the atoms are no longer electrochemically neutral. One will become positively charged because it lost electrons, and the other will become negatively charged because it gained them. So in any case, an ion is a positively or negatively charged atom. I have the plural form of the word up there for some reason. Technically, we have cations and anions. Do not worry about that, but those are the special names for the positive and negative versions of them. Kind of like cathode and anode on a battery, the positive and negative end. So here's an example of an ionic bond and an ionic compound. Salt, again, sodium chloride. So the chlorine atom takes one electron away from sodium and it keeps it. It belongs to the chlorine atom. It stays orbiting around its nucleus. That makes the chlorine atom negatively charged, and the sodium atom, it now has a mismatch in the number of protons versus electrons. It'll have 11 protons still, because that's the definition of sodium, but then it will have only 10 electrons. The other type of bond is the covalent bond. So this is created by the sharing of electrons. So rather than an electron being permanently transferred from one atom to the next, instead the electron will orbit between them. I don't have a video of this I can show you, but the electron, like I said, pairs of electrons actually will orbit back and forth between two or more atoms, and that's what holds them together. Now, because of that interaction, covalent bonds are comparatively much weaker than ionic bonds. A fairly good practical way to measure the strength of an ionic bond is to find out what the material's melting point is. Sugar, if you placed sugar crystals on a pan and heated it on your stovetop, well, they would melt fairly quickly, and it would even do what we say, or what we call decompose, where the hydrogen and oxygen would be released from the sugar, the carbon stays behind. That's why burnt sugar looks black, because burnt sugar is actually just carbon. And that happens at fairly low temperatures. If you did this same thing with salt, you would not get that material to melt. Salt has a melting point somewhere around 900 to 1,000 degrees Celsius. We have a special term, molecule. So compounds that are formed by covalent bonds, those are molecules. So the things we looked at earlier, proteins, carbohydrates, lipids, those are molecular compounds. Living things are made of molecular compounds because the bonds are weaker, it takes much less energy to break those bonds apart. Well, life, the busyness of the chemistry within you, in your cells are constantly breaking things apart and building them into new things, breaking apart carbohydrates for energy, building up proteins to build your body or to do whatever. We have to use low energy compounds for that. So life is made out of molecules. The energy to break apart ionic compounds would be much too great for life to be possible, I suppose we could say. So that is a very simple take, but this is a biology class. We only really need to know the basics to be able to move forward. Next time, we're going to talk about the specific properties of the water molecule and how that is related to life, and also discuss acids and bases a little bit. Thanks for watching.